Let's look at the type of values that are used when doing statistics. When we're conducting a study, we usually care about the parameters of a population. That's all the individuals or items of interest, but we can't measure them all because it's not feasible or practical. We therefore usually measure the values for a subset and calculate statistics of a sample. And our sample statistics are therefore estimates of the population parameters, as indicated in the diagram here, where we want to know about the entire population. We take a sample, calculate its statistics, and then use those statistics to estimate the population parameters. So we then need a way to summarize the sample or population, because populations and samples usually have too many values to make sense out of every single one of them. And we usually want to know the basic properties anyway, not every single value. For example, if we wanted to see whether a disease raised the diastolic pressure of individuals with it, do we really need to look at all the numbers individually, or does the average accomplish the goal? In the box shown, we can see sample data sets of blood pressure values for baseline and then for individuals with the disease. And if we looked data value by data value, first of all, it would be too overwhelming. And second, if we looked at the first couple of values or the last couple of values, we would actually see that the first set of values seems to be larger than the second. Only when we calculate an average for all the values together do we see that the second set has an average or typical value that is larger than the first set. So we usually want to calculate basic properties like this for a sample or for a population. So what basic properties do we calculate? What are the basic properties of data sets that we typically want to know? Well, first, we want to know about the location. What is the typical value or average value? Second, we want to know about the spread of the data. How variable are the data values? And third, we sometimes want to know how the distribution of values compares to others that have similar locations and spreads. First, let's look at statistics of location. So here we're asking the question, what is the typical value or the average? The first important thing is to realize there is no the average. There are 4 different averages that can be calculated. The first is the mean, which is the sum of all the values divided by the number of values. The second is the median, which is the value that's in the center of our data set, with half on each side. The third is the mid-range, which is halfway between the smallest and largest value. And the fourth is the mode, which is the most frequent or common single value. You can have more than one mode if more than one value are equally common. The first 2 are commonly used, and it's always important to know which one someone is talking about when they're talking about the average. And the last 2 are rarely used, so we won't focus anymore on that. The mean and median are the most common statistics of location, and we'll take a look at them here with this data set consisting of a 2, an 8, an 11, 12, 13, and a 14. For the mean, we'll sum all the values and divide by 6, because that's how many there are. For the median, we would look at the particular value halfway through the data set, so that would be between the 11 and the 12. So the mean uses the exact positions, and you can think of it as calculating something like a center of mass, where values like that 2 that are far out to one side will pull the mean in their direction. The median just divides the data into regions, upper and lower, and doesn't really take into account where they are located relative to each other within those regions. And both provide a location that the values are ranged around, as you can see in the figure. Here's the same kind of figure, but now I have a more asymmetric data set with a 2, a couple of 3s, a 4, a 7, and a 20. And now you can see how the median and the mean are becoming a bit more different because the mean is being pulled upwards by that large value, the 20. And this figure illustrates why we must be aware of the average that someone is using. In this case, this value of the 20 is bringing the mean upwards away from the median, and the mean no longer represents where most of the values are because of that extreme value. For this data set, if someone wanted to make the average value seem small, they would use the median, but if they wanted to make the average value seem large, they would use the mean. So you always have to be aware of which average someone is talking about when they're describing a data set where you can't see all the values, they're just telling you the average. An important thing to think about when we think about statistics is what the properties of those statistics are. And a major property is how robust, that is consistent or resistant to the effects of randomness, are the values that we're calculating. So one way to think about this is what happens to the statistic in the presence or absence of outliers, which are rare extreme values like we saw in the previous slide. The mean, as we saw, is not robust. The median is robust because it's only looking at the middle. It's, by definition, ignoring the extreme values. The mid-range is not robust because in fact the only values being used to calculate it are the smallest and the largest single values. And then the mode typically is robust because it's based on most common values, so outliers would not show up. Another way to think about how robust something is how consistent is it when calculated from repeated samples from the same population. In this case, the mean and the median are both robust. Now the mean is robust because it's using the maximum amount of information. It's using the location of every single value. The mid-range is not robust because it's only using 2 values, and the mode, in this case, is also not robust. In particular, if the distribution has a lot of equally common values, the mode might be all over the place in different samples. Now for statistics of spread, also called variability or dispersion, and now we're asking the question, how variable are the values? So we'll look at 6 different spreads. The first is the range, which is just the distance from the smallest to the largest. Second is the interquartile range, which is the width of the middle 50% of the values. And then we'll look at 4 values that are all based on the sum of squares, which is the sum of square differences from the mean. The variance is based on the sum of squares, and you can think of it as the mean of the sum of squares values. The standard deviation is going to be the square root of the variance, and the coefficient of variation is the standard deviation relative to that mean. First, the range and interquartile range. The range is just the difference or the distance between the smallest value and the largest value. In this case, it would be 14 minus 2 is a range of 12. And the range is not robust because it's only using 2 of the values. The IQR, which represents the middle 50%, in this case you can see it's encapsulating the middle 3 out of the 6 values, is more robust because it uses quartiles and it's related to the median in a way we'll get into in just a moment. Here are the same statistics of spread, the range and interquartile range, for a different data set, our data set that has that large 20. You can see now how the range is greatly inflated, now it's 18, whereas the IQR is still fairly small because the middle 50% of the data is fairly close together. As mentioned, the IQR uses quartiles to determine its value. So what do quartiles do? These divide the data into 4 equal regions, and the median is actually one of these quartiles. That's dividing the data into a top half and a bottom half. And then we have Q1, which is the first quartile, and that's going to divide the bottom half into 2 equal-sized chunks. You can also think of this as being placed at the 25% spot. Q2 is our median, placed at the 50% spot. And Q3, our third quartile, is placed at the 75% spot, and that's dividing the top half of the data into 2 halves. And the IQR is going to be the value of Q3 minus Q1. In this example, with 8 data values, you can see the median is in between the 4th and 5th value, and then in the bottom 4 values, Q1 is in between the 2nd and 3rd, and in the top half, the Q3 is in between the 2nd and 3rd out of those 4 values. The quartiles are fairly straightforward to figure out if you have an even number of values like this. If the dataset has an odd number of values, it's a little bit more complicated. So the median can then be the individual single value that's in the middle. So for example, with this dataset of 7 values, the median is the 4th out of 7. Now Q1 will be the median of the bottom half, and we'll include the median in that bottom half. So for those 4 values, Q1 is in between the 2nd and 3rd, that is the 4 and the 7. And for the top half of the data, Q3 is in between the 12 and the 15. And then again, the IQR would be Q3 minus Q1. So to recap how to calculate quartiles using a simple method, the method's going to ignore the shape of the distribution and just focus on the values. Step 1, we'll arrange the values in order from smallest to largest. Step 2 depends on whether n, the number of values, is odd or even. If n is odd, the median will be the center value, and we'll include this value in both halves during step 3, our calculation of Q1 and Q3. If there's an even number of values, the median is the middle of the 2 middle values. Because this median is not an actual data value, we would not include it when we're doing step 3. And then in step 3, we're going to repeat either step 2a or 2b, depending on whether the top half and bottom half of the data set have an even or odd number of values. And then Q1 would be the median of the smallest half of the values, and Q3 would be the median of the largest half of the values. So it turns out that other methods exist because the definition of the median is actually arbitrary. There's no good theoretical foundation for it. If the exact quartile values are important, make sure you know which is being used. So there's an alternative number 1, which is same as the previous method described, but we would not include the median when we're calculating Q1 and Q3 when we have data sets with an odd number of values. And then a second alternative, we would calculate Q1 and Q3 using a weighted average of the data points if the data set has an odd number of values. So if the data set can be represented by 4n plus 1 values, so that would be 5 values, 9 values, 13 values, etc. Q1 would be 25% of the nth value and 75% of the n plus 1th value. And Q3 would be 75% of the 3n plus 1th value and 25% of the 3n plus 2 value. If the dataset has 4n plus 3 values, so that would be 7 or 11 or 15 values, etc., Q1 would be 75% of the n plus 1th value and 25% of the n plus 2th value. Q3 would be 25% of the n plus 2th value plus 75% of the n plus 3th value. This is obviously a more complicated way to do it, so most people would go with the two methods described previously. However, this method does take the shape of the distribution into a bit more account. If you're using a computer software program to calculate your medians, you'll want to make sure you understand which one is being used. Now for the other 4 statistics of spread: the sum of squares, the variance, the standard deviation, and the coefficient of variation. So medians and quartiles are used for describing data sets, but these are the values that are used in statistical tests due to mathematical properties of sums of squares and variances. First up, the sum of squares, which is the sum of the squared differences from the mean. So if we look at our data set here with 6 values, if we calculate the mean, we get an 11. So then our sum of squares is going to be looking at each of those 6 values and calculating the sum of the squared difference between each value and that mean. So that first value would be 6 minus 11, which is negative 5 squared. Second value would be 8 minus 11, which is negative 3 squared, and so on, and then we would add them all up to get 60. Looking at a slightly different data set that has the same mean, but we can see is more spread out, our sum of squares would be the 2 minus 11, which is negative 9 squared, plus the 6 minus 11, which is negative 5 squared, and so on. And we would get a sum of squares of 200, which is much larger than the 60 we got for the previous dataset. Here we can see a dataset where most of the values are much closer together, but one is much larger than the others, and if we calculate the sum of squares, we'll get a 235, which is even more than the one in the previous slide. And this illustrates one of the unfortunate properties of the sum of squares is that it is very prone to being inflated by the presence or absence of outliers. Single values that are much larger or smaller than the others can have a large impact on the sum of squares. So to recap, the sum of squares is the sum of the squared differences from the mean. This is the foundation of the variance, standard deviation, and coefficient of variation that we'll talk about in a second. It's extremely prone to being inflated by outliers, which is unfortunate. However, the variance, the next statistic we'll talk about, has a useful property that for 2 independent datasets, the sum of their variances is the same as the variance of the combined dataset. This mathematical property is so useful that it causes us to use sum of squares and variances despite this problem it has with outliers. Okay, now for the variance, and this is represented by the Greek sigma symbol, or S, and then with a square. The variance is always positive, because it's based on a sum of squares. It's not robust to outliers, since it's going to be based on the sum of squares. If we have a population of data, we represent the variance with sigma square, and it's the sum of squares divided by n, where n is the number of data values. However, if we have a sample, we represent the variance with s squared, and we have the sum of squares divided by n minus 1. We use this second equation for a sample because the estimate of a population variance using a sample often underestimates the true population variance. Therefore, the different denominator is used to create what's called an unbiased estimate of the population variance. Remember that all sample statistics are estimates of population parameters, and so we'll never expect them to always be exactly correct, but we don't want there to be any bias where they consistently underestimate or overestimate, and this adjustment to the variance formula prevents it from consistently underestimating the population variance. Now for the standard deviation, represented with the Greek symbol sigma if we're looking at a population, or S if we're looking at a sample. It has the same properties as the variance because it's just the square root of the variance. And the standard deviation now has the same units as the original data. Unlike the variance, if you think about it earlier, because everything was squared, any units that our data values would have had would have become squared, which actually makes the variance hard to interpret. The standard deviation, however, now the units are back to the original dataset and it's much easier to interpret. For this reason, the standard deviation is used as a descriptive statistic much more than the variance is. Our last measurement of spread is the coefficient of variation, sometimes referenced with the value CV. It has the same properties as the variance, because it's based on the variance. For a population, we're going to take the population standard deviation, divide by the mean, multiply by 100 to get a percentage. For the sample, we'll take the sample standard deviation, divide by the mean, multiply by 100 to get a percentage. And this puts the variation into context. How variable is the data compared to the typical value? It's often used as a descriptive statistic, it's not particularly common, and it's rarely used in statistical tests. It's used enough, however, that you should be familiar with it. Before we move on to the discussion of the shape statistics, there's something you should be aware of. There are two different equations that can be used to calculate the sum of squares, as shown on the top right of this slide. There's the summation of the squared differences, which is fairly straightforward, and then there's that second equation, which is the sum of the squared values minus the sum of the values squared, all divided by the sample size. Both of them will give you the exact same number with a particular data set, as you can see in the example shown on this slide here, for a data set of 3, 4, 6, and 7, which has a mean of 5. The first equation is much easier to understand and visualize what it represents, whereas the second seems more complicated. However, if you're doing calculations using a calculator and doing it by hand, the second equation requires less button pushing, has less rounding error, and will actually give you a more accurate value. Because people used calculators before we had computers for such a long time, that second equation was used quite a lot, and is therefore still written in a lot of textbooks. Now for the statistics of shape, and what we'll be doing is comparing the shapes we see for our data to the normal distribution, i.e. the bell curve, which is a baseline shape for comparison. So there are 2 or 3, depending on how you think about it, different shape statistics. There's the skewness, which is going to measure asymmetry, and the kurtosis, which is going to measure peakedness. What it really does is measures the thickness of the tail, however. And then a value called the excess kurtosis, which is just the kurtosis minus 3. The skewness is calculated by that equation there, which is the sum of the cubed differences between each data value and the mean divided by the number of data values. And then we have to scale that for the variation by dividing the whole thing by the standard deviation to the third. And what this does is it measures asymmetry. If we have a perfectly symmetric distribution, like shown in the middle, we'll get a skewness of 0. If there's a tail that moves off to the left with a small number of values that are much smaller than what most of the values are, we'll get a negative skewness. And if we have a tail that goes off to the right, where there's a small number of values much larger than the typical value, we'll get a positive skewness. The kurtosis, which measures the peakedness or thickness of the tails, is a very similar equation, but now we have the 4th power instead of the 3rd power. If you calculate the kurtosis of the normal distribution, as shown in the middle, you'll get a kurtosis of 3. So if we subtract 3, that would give us an excess kurtosis of 0. We would call that distribution mesokurtic, meso for like middle. If you have a peaked, kind of pointier distribution with skinny tails, the kurtosis would end up being larger than 3, excess kurtosis would be positive, and we would call that leptokurtic. Whereas on the left, if the distribution is kind of fatter with tails that have more values in them, we would get a kurtosis that's less than 3, which would be a negative excess kurtosis, and we would call that platykurtic, platy meaning flat. The exact values of kurtosis are often not used directly. We're really just comparing them to the 3 for kurtosis or the 0 for excess kurtosis to figure out whether our distribution looks like the normal distribution, that is mesokurtic, or whether it looks like it's leptokurtic or platykurtic. The equations for skewness and kurtosis on the previous slides were for the population of data. Estimates of the population skewness or excess kurtosis from sample data can be biased, and so the equations shown in this slide are better. For the skewness, we have 2 options for equations to use. For the excess kurtosis, we have 1 to use. And these will allow our sample data to estimate a population data in a way that is not consistently too large or consistently too small. What's the application of the skewness and kurtosis? The skewness and kurtosis are rarely studied for their own sake. They're usually calculated to see if the distribution is normal, which is typically what we want, because most statistical tests require normal distributions for our data sets. So what we usually really want is for the skewness to be 0 and the excess kurtosis to be 0, so that we can be confident our statistical tests will work. So here's kind of a summary of our 4 different location statistics, our 6 different spread statistics, and our 2 different shape statistics. The mean, median, and standard deviation are often used when describing data. The range, IQR, and coefficient of variation are also sometimes used, but not as much. And then for doing statistical testing, most statistical tests work with the means if they're interested in location, and variances if they're interested in spreads. And then the skewness and kurtosis are often prerequisites for doing our tests. So there you have it. That's an overview to the basic statistics that are calculated for a population of data, but much more commonly a sample of data that we're trying to use to estimate the values for a population of data. There's a companion video to this one, linked to in just a second, that goes through a step-by-step example using a data set and calculates all the values shown. Click at the top to subscribe to the channel. On the left is a link to the playlist for stats examples, and on the right is the video I mentioned that walks through calculations of all the statistics discussed in this video.